Welcome everyone to this Monash Cybersecurity Seminar. Today we are very happy to welcome Nguyen, who is a fourth-year PhD student at IBM Research Europe, Zurich, and ETH Zurich in Switzerland, supervised by Dr. Vadim Lubashevsky and Professor Dennis Hofheinz. Previously, Khanh obtained his bachelor's and master's degrees in mathematics and computer science at the University of Bristol in the UK. And he is in general interested in lattice-based cryptography and its efficient constructions. And today his talk will be related to that. And in particular, he will talk to us about lattice-based zero-knowledge proofs and applications, shorter, simpler, and more general. Thank you, Khanh. The scene is yours.
Okay, so can you see my slides?
No, you haven't shared them.
Okay, I need to share again. Okay.
Yeah, yes.
Okay, so can you see my slides now?
Yep. Yeah, all good.
Okay, so thank you very much for the introduction, and thanks everyone for coming. I know, like in Australia, it might be a bit late. So, hi, my name is Khanh, and today I'm going to talk about lattice-based zero-knowledge proofs and applications. So this is joint work with Vadim Lubashevsky and Maxime Planson. Okay, so let's start with zero-knowledge proofs. I guess everyone is familiar with this concept. So we have some statement. We have two parties, the prover and the verifier, and the prover wants to convince the verifier that a certain statement is true. So the prover has the corresponding witness. They engage in an interaction where they send messages to each other. And at the end, the verifier outputs accept or reject, meaning that the verifier is either convinced or not that the statement is true. So we have a few properties of zero-knowledge proofs, like completeness, which says that if the witness is valid, then the verifier should accept. Soundness, which says that if the witness is invalid, then for any cheating prover, the verifier should reject. And zero-knowledge, which says that the verifier shouldn't learn any information about the witness from the interaction. By the way, just if you have any questions, just interrupt me at any time. Okay, so so due to the significant progress in building quantum computers, there has been a tremendous amount of interest in making cryptographic primitives quantum safe. So it's highly evidenced by the ongoing NIST post-quantum competition, where recently they announced that 4 schemes will be standardized by NIST. Out of them, like there are 3 based on lattices. Okay, so there's already a question. Let's see. Oh, okay.
No, I wrote that.
Okay. Would it be okay if you could interrupt me if there are any questions?
Yes. Yeah, I can. I'll monitor the questions.
Okay, thanks. So it looks like lattice-based constructions are seem very attractive because not only do they offer relatively small sizes, but they can also be very efficiently implemented in practice. So it seems that lattices are a suitable choice for building more advanced privacy-preserving primitives, such as zero-knowledge proofs. However, if we look at the current state-of-the-art quantum-safe zero-knowledge, then we can see that the most efficient ones are based on hash functions. So here we have Ligero, Aurora, and Fractal, where the latter two provide polylogarithmic proof sizes. And then concretely, they achieve around 200 kilobytes. In terms of the prover runtime, they run in the order of minutes, 3 to 5 minutes. So it looks nice. However, if we look on the lattice side, then okay, we already have some constructions which achieve sublinear proof sizes, but they are still of theoretical interest. For example, this lattice adaptation of bullet proofs achieves polylogarithmic proof size. So the reason why they're only of theoretical interest is that if one were to literally just instantiate them with concrete parameters, they would easily be around tens or hundreds of megabytes. But however, as we can see, it's a very active area of current research because there are already like 2 papers at this year's crypto, which are in this area, and they also provide some concrete proof sizes. So the first one is achieves square root proof size asymptotically, and it's around 6 megabytes, which already beats Ligero. But then there's also another scheme which achieves polylogarithmic proof size, and it's in terms of concrete proof size, it's around 30 megabytes. So you can see that there is still a long way to go to be at least comparable with the hash-based proof systems. Okay, so it seems that for proving arbitrary statements, the best choice are the hash-based proof systems. However, there are still some aspects where lattice-based constructions could outperform these protocols. So first of all, the hash-based proof systems include a so-called startup cost or a base cost, which is around at least 50 kilobytes. So obviously, if you want to prove very big statements, then 50 kilobytes shouldn't be much. However, if we just want to build an identification scheme or get a signature scheme out of it, then 50 kilobytes it's a lot compared to what we can achieve now. Also, they are not very fast because one has to perform a lot of hashing, and they also require a lot of memory, since these constructions make use of error correcting codes, which operate on code words of the size linear to the witness size. So these are weaknesses, let's say. So in terms of research directions in the lattice world, obviously the one obvious one would be to construct succinct, let's say, logarithmic size zero knowledge proofs from lattices, which can be hopefully much faster than the hash-based ones, and also they could be comparable in terms of the proof size. So that's one clear direction, and we can see that there are a lot of people interested in this area. So it's a very active area of current research. However, what we discuss in the paper or in this talk is to construct, even though they're asymptotically linear, but practically efficient zero knowledge proofs, let's say concretely meaning less than 50 kilobytes, which is the base cost for these hash-based proof systems for specific type of statements. So that's our goal in this talk. So what do we mean by interesting statements? So if we want to build some privacy oriented primitive from lattices, then it makes sense that at some point, some user or some entity will prove knowledge of a short vector in a lattice. So at the end of the day, we really want to prove something like AS is equal to U or some related equation. So yeah, just think of it as equation over some ring R, where R is, let's say, integers modulo Q, or some polynomial ring. And as I said, S is small, meaning that, let's say, the norm of S is small, or S has small coefficients, let's say between -1 and 1. Okay, so if we look at the prior works on proving AS is equal to U, if we consider linear sized lattice-based zero knowledge proofs, then we can split them into two categories. The first one is the approximate ones, which stem from works by Lubashevsky. So they are called approximate because we don't really prove that AS is equal to U and S is short, but we prove that S is slightly larger, but still relatively short, as well as some factor C, such that AS is equal to CU. So obviously it is not really what we started with, right? However, it turns out that it's enough to build some simple primitives such as identification schemes, and that's basically the core part of the Deletheum signature. So in terms of proof sizes, well, they produce pretty small proofs. However, there are still some cases, some scenarios where we really want to prove things exactly. So we want to prove that indeed AS is equal to U, or that coefficients of S are small. So for example, if we look at this equation, AS is equal to U, and treat U to be the ciphertext, then we want to prove validity of the ciphertext, then we wouldn't be really interested in proving that C times the ciphertext is valid. Or if we want to commit to our vote, which is either 0 or 1, then we wouldn't be interested in proving that it's between -100 and 100, right? So we can see that there are still some applications where we want to prove things exactly, and unfortunately, this results in much bigger proof sizes. So here is let's say, the benchmark which was used in prior works. So this is the equation over integers modulo Q, Q is around 2 to the 32, and prove that AS is equal to U, where SIs have ternary coefficients. Vector S has length 2048. So we can see that there are many like protocols which can prove this benchmark, but the best ones, which are in the last two columns, use so-called entity packing technique, and they achieve less than 50 kilobytes. So in the next 10 minutes, I will try to describe the idea behind the entity packing technique and behind these protocols, and we'll discuss their advantages and disadvantages. Okay, so to explain the idea behind the entity packing technique, we need the following setup. So consider the standard polynomial ring RQ equal to ZQ of X modulo X to the D plus 1, where D is a part of 2, and now we want Q to be 1 mod 2D. So why is it the case? Because then we can write X to the D plus 1 as the product of linear terms modulo Q, X minus R1, X minus R2 up to X minus RD, where I will call Ri's the roots of unity. And now, given the polynomial A in RQ, we define entity of A to be the vector A hat equal to the evaluations of A in the roots of unity. So entity stands for number theoretic transform. Okay, so we have this definition of entities. So by definition, we have two nice properties like homomorphic properties. The first one is, which is not written here, but it's obvious, entity of A plus B is entity of A plus entity of B. And then the second one is entity of A times B is equal to entity of A, the component-wise product, entity of B. Okay, so the main strength of this entity packing technique is that we can efficiently prove that coefficients of some vector, integer vector, lie in some certain range. So to showcase this idea, we will prove that some vector S has binary coefficients. So I have this homomorphic property on the right-hand side. Okay, so the idea is as follows. So I want to prove that this vector S has binary coefficients. So I will define S check to be the polynomial such that entity of S check is equal to S. And then we can see that from this homomorphic property that S has binary coefficients if and only if S check times S check minus 1 is 0 over RQ. So basically, we reduce this problem to proving that S check times S check minus 1 is 0 over RQ, which we will call the product proof. Okay, so how do we do that? We commit to S check. So we follow this commit and prove approach where we commit and then prove the relations between the committed messages. So we commit to S check, and here we have like a slight problem. So even though the vector S had small coefficients, well, binary, it doesn't mean that S check will also have small coefficients. And because S check can have large coefficients, it means that we can't use the standard compressing lattice-based commitment scheme. So instead, we have to use a slightly more advanced one, which will be the homomorphic commitment BDLOP. We will call it BDLOP. So we commit to S check. And now the idea is that the prover, so at some point in the protocol, the verifier sends alpha, and we send Z equal to Y plus alpha S check, which we call the masked opening of S check. So what's the idea now? Okay, so we can see that the verifier who's given alpha and Z, they can compute Z times Z minus alpha. And then you might see, okay, what is this random expression? So it is not very random, because if we write this expression as a quadratic equation in alpha, then the quadratic term will be exactly S check times S check minus 1, which what we want to prove is 0. So basically, we want to prove that the quadratic term in Z times Z minus alpha disappears. Okay, so we have this expression on the right-hand side. So now we commit to the Y. We send the commitments to the constant and to the linear term of that expression Z times Z minus alpha. Then, as that's the step we discussed before, given the challenge alpha, we output Z equal to Y plus alpha S check. And then there are two things. First, we want to prove that Z is well-formed. that Z is indeed Y plus alpha S check. And to prove that, we just prove that Z minus Ty plus alpha Ts is a commitment to 0. And that holds because we assume that we use the fact that BDLOP commitment is homomorphic. And then the second step is proving that the quadratic term in Z times Z minus alpha vanishes. So we do this by proving that Z times Z minus alpha minus T0 plus alpha T1 is a commitment to 0. Okay, so that was the overview of the product proof. Okay, but if we want to prove something similar to the benchmark statement, we want to prove shortness and also prove some linear relations. So suppose we also want to prove that AS is equal to U. So the idea is that as before, the prover will send Z equal to Y plus alpha S check. So what can we do from that? So we can see that if alpha is an integer, then we can apply entities on both sides to get that Z hat is equal to Y hat plus alpha S. And then because we have S on the right-hand side, we can multiply both sides by A, and we get that AZ hat is equal to AY hat plus alpha U. So that's the main observation. So what we are going to do is we will send AY hat at the beginning. Then the verifier will send alpha, we send Z, and then the verifier can check that AZ hat is equal to AY hat plus alpha U. So let me just repeat that. Yeah, so the hats is the entities. Yeah. Okay, so we send this masking Y. We output now W equal to AY hat. Given the challenge alpha, we send Z equal to Y plus alpha S check. And then we prove that Z is well formed, meaning that Z minus Ty plus alpha Ts is a commitment to 0. And then the verifier checks that AZ hat is equal to W plus alpha U. So I guess it was a slightly simpler protocol than the product proof. So that's the overview of the linear proof. Okay, so what are the bottlenecks of sorry.
Can I ask a question?
Sure.
So here you really sorry. You really need that the alpha is invariant under the entity mapping, right?
Yeah, exactly.
Okay.
So yeah. Okay, so so what are the bottlenecks of this approach? So that's the original BLS 19, Young et al. 19 protocol. So first of all, because we wanted to do this entity packing and introduce this S check, which has big coefficients, we had to use this BDLOP commitment. And it is relatively expensive. So why is it the case? Well, it's definitely not compressing because the commitment size is linear in the message size. This means that if we want to commit to a long vector, then the commitment itself will be long. The second problem is a little bit technical, and we didn't really discuss that, but also, obviously, at the end, we want to prove validity of the commitment. So we perform some opening proof of the BDLOP commitment scheme. And to do this, we need a challenge space, which has the property that for any two distinct challenges, the inverse is invertible over RQ. And because we have this ring where x to the d plus 1 splits into the linear terms, the authors had to pick this small challenge space, which satisfies this property. So it is the challenge space of monomials. We can see that the size of it is 1 over 2d, and the protocol needs to be repeated 128 divided by log 2d times, which is a lot. Another thing is that we have to send that vector z in a clear, which is of the same length as S check, which will be of the same length as S. So if vector S is long, then Z will also be long. And then if we want to prove a degree K equation, so in the previous slide, we had K equal to 2, then the prover needs to send K garbage commitments Ti. So we have T0 and T1. Okay, so these are the, let's say, main disadvantages. But in the following year, we had, first of all, we have the ALS 20 paper where they proposed a new BDLOP opening proof where they reduced the soundness error from 1 over 2D to 1 over Q, which is let's say, significant. Secondly, they introduced a new product proof where you don't need to send this Z in the clear. And also they reduced the number of garbage terms by 1. However, if we want to combine ALS20 with the linear proof from the previous slide, then we would still need to send that Z in the clear, right? So the follow-up work, the ENS20, also with Muhammad, describes a way to prove linear relations where we don't need to send that vector Z. So it's pretty nice. So if we combine ALS20 with ENS20, we already get less than 50 kilobytes of proofs. Okay, but there are still some, some bottlenecks of this protocol. So we can see that because we wanted to do this entity packing technique, we still have to use the BDLOP commitment. And also this expensive part of the protocol, which is the opening proof, needs to be repeated 128 divided by log Q times. So yeah, so these are the consequences of using the entity packing because, well, the soundness was 1 over Q because x to the d plus 1 splits into linear terms. So now the question is if we really need the entity packing technique to improve this protocol. Well, you could guess that if the answer was yes, then we probably wouldn't be here. So I know from Muhammad that that in Australia people probably wouldn't be on the beach because it's getting cold. But yeah, you could guess that the answer is no. So that's what we propose in this talk. So lattice-based zero knowledge proofs where we don't need to rely on the entity packing technique. So to describe the idea, so consider the following setup. So consider the polynomial ring RQ ZQ of x modulo x to the d plus 1, where q is a power of 2 and q is 5 mod 8. So it is, I can just pick 5 mod 8. So then x to the d plus 1 factors into 2 irreducible polynomials of degree d over 2. And also for the later part of the presentation, let me define the automorphisms. So for alt I define sigma I to be the automorphism defined by sigma I of x equal to x to the I. And let me just pick sigma equal to sigma minus 1. So that's the only one we will need in this presentation. Obviously, it seems a bit random why it's sigma minus 1, but it will be interesting and useful later. So we have the following roadmap. First, we define the ABDLOP commitment. So we will use the ABDLOP commitment, which is just a combination of the ITI commitment, the standard compressing commitment, and the BDLOP one. So the idea is that we will commit to these long vectors, using the ITI part of the commitment so that the commitment is compressing. However, we could see that in the protocol, sometimes we commit to these auxiliary garbage polynomials. And that's where we use the BDLOP part of the commitment to commit to these small polynomials. The second part is proving quadratic equations over RQ. The third part is we show how we use these quadratic proofs to prove inner products over ZQ, either with one unknown, so like, I don't know, inner product of S times A, or inner product between two unknowns, like the inner product of S and S. Then we show how to, we introduce the, well, not introduce, but we recall the approximate range proofs technique to prove that certain equations hold over integers. And then we just combine all these ingredients if we have time, hopefully. Okay, so we start with the ABDLOP commitment. So as I said, it's a combination of the ITI and the BDLOP commitment. So what do we mean by that? So suppose we want to commit to a polynomial vector, which we split into two parts, the S1 and M. S1 has length M1 and M has length L. And S1 has small norm, and we will see why. But M can be arbitrarily big. So the ABDLOP commitment under randomness S2 is defined as, so we have two parts. The first one is TA, which is equal to A1 S1 plus A2 S2. And then we have TB, which is equal to BS2 plus M. So we can see that it's a generalization of these two commitments, because if L is equal to 0, then ABDLOP is just the ITI commitment. So if L is equal to 0, then M, there is no M. There is no B, there is no TB. So we just have TA, which is equal to A1 S1 plus A2 S2, which is the ith commitment. On the other hand, if M1 is equal to 0, then there is no S1. So there is no A1 S1. So we have TA is equal to A2 S2. TB is equal to BS2 plus M, which is the BDLOP commitment. So in terms of security, well, it's the same proof as the prior prior commitments. So binding implies finding a C solution to A1 S2 by subtraction. It also satisfies the notion of weak binding or relaxed binding used in prior papers using the same techniques. And then hiding follows from LWE because that's this part A2B times S2 can be pseudo-random for long enough randomness. Okay, and now maybe just like 1-2 slides about how to perform the ABDLOP opening proof. It's just going to be like a standard approximate proof. There's nothing nothing new. So we want to prove that we know the opening of the commitment. So we know S1, S2, and M. S1, S2 has small coefficients. So what we do is we just, so the prover generates the YIs. They send W equal to A1, Y1 plus A2, Y2. The verifier picks the some challenge C, and the prover sends ZI equal to YI plus CSI. There should be some rejection sampling happening to keep the protocol zero knowledge, but we'll ignore that for the simplicity of this talk. Then the verifier checks that Z1, Z2 are small and that A1, Z1 plus A2, Z2 is equal to W plus CTA. So that's basically the standard approximate proof, like Schnorr. Okay, but we won't really use this slide too much, so it's fine. Okay, so the next step in our presentation is proving quadratic equations over RQ. So we can prove arbitrary quadratic equations, but for simplicity, let me focus on proving S1 transpose S1 plus M transpose M is equal to 0. And on the top right, we have this ABDLOP commitment to S1 and M. So the strategy can be, it's pretty similar to the one I described earlier. So, okay, so this is the ABDLOP opening proof. So that's literally the protocol we had on the previous slide. And okay, so what's the intuition? Okay, so we can see that the prover sends ZIs equal to YI plus CSI. So now if I compute Z1 transpose Z1, and I look at it as a quadratic equation in C, then we see that the quadratic term in C is indeed S1 transpose S1. So it is one component which is included in this equation we want to prove. So that's nice. But we can't really do the same with M, right? Because we don't send any mass opening of M. We don't send any Z equal to Y plus CM. But the observation here is that we know that TB minus BZ2, just by computation, TB minus BZ2 is equal to minus BY2 plus CM. So we can use this identity we just multiply TB minus BZ2 transpose with TB minus BZ2. And I look at this equation as a quadratic equation in C, and I can see that the quadratic term in C will be M transpose M, which is another part of the equation I want to prove. Okay, so I can just sum these two things. So Z1 transpose Z1 plus TB minus BZ2 transpose TB minus BZ2. And I obtain some quadratic equation in C squared in C, where the quadratic term is indeed S1 transpose S1 plus M transpose M. So at the end, I just want to prove that this quadratic term disappears. So the strategy is basically as before. So I send commitments to these GIs and prove that Z1 transpose Z1 plus TB minus BZ2 transpose TB minus BZ2 minus T0 minus CT1 is a commitment to 0. So that's basically intuition is almost the same as before. Okay, so what do we mean by committing to GI in this ABDLOP setting? So what I mean by committing, I mean appending the ABDLOP commitment. So basically, I can commit to G0 and GY by sending T0 equal to B0 transpose S2 plus G0. And then T1 is B1 transpose S2 plus G1. And by appending, we can see that the whole thing is still a valid ABDLOP commitment to the message S1, M, G0, and G1. So that's kind of a nice thing. So that's what I meant by that we have the I-type part where we commit to S1, and then we have the BDLOP part where we commit to these intermediate auxiliary polynomials. Okay, and this protocol is not very optimal because we send two garbage terms. We can use the AALS20 trick where we can send only one garbage commitment instead of two. Okay, so that was basically, well, I can see that there was nothing new. It's just adapting the product proof to this ABDLOP setting. But now let's mix it up a bit. So suppose we want to prove quadratic equations with automorphisms. So I know it sounds a bit random, but we'll see on the next slides why it's interesting. So suppose that we want to prove that S1 transpose sigma of S1 plus M transpose sigma of M is equal to 0. So now the intuition is that if we force the challenge space to have the property that each challenge C is stable under the sigma automorphism, then we can proceed literally as before. So why is it the case? Because, well, so I can now write, instead of Z1 transpose Z1, I write Z1 transpose sigma of Z1 plus TB minus BZ2 transpose times sigma of TB minus BZ2. Okay, so if it wasn't clear, when I say sigma applied to the polynomial vector, I mean sigma applied to each polynomial in the vector. Okay, so I have this equation and I write it as a quadratic equation in C. So if I just write everything down, if I just expand this equation, then you will see that there are a lot of, there will be some sigma of C floating around. But if I assume that sigma of C is equal to C, then I can write everything as a quadratic equation in C, where this quadratic term will be exactly S1 transpose sigma of S1 plus M transpose sigma of M. And then, okay, the G0 and G1 terms are a bit more complicated, but it doesn't matter. So here we really use the assumption that sigma of C is equal to C. So is it feasible? Okay, so we have some conditions on the challenge space. So the first one is for the soundness, we need very large, exponentially large challenge space. Then we want sigma of C equal to C for any challenge C. And also for soundness, we wanted this, well, this technical property that any difference of distinct C and C prime should be invertible over RQ. Okay, so what we will build, okay, let me just define the challenge space. So, okay, it might sound a bit, might look a bit scary, but what's happening here? Okay, I pick C0 plus C1 plus blah, 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 C d over 2 minus 1, x to the d over 2 minus 1. So that's kind of, let's say, the first part of the polynomial. Then there is no x to the d over 2, as you can see. And then you could see this, the second part of the polynomial as the reflection of the first part with the flipped sign. So here we have minus c d over 2 minus 1, x to the d over 2 plus 1, and so on. And the last term is minus c1, x to the d minus 1. And these coefficients are between minus kappa and kappa. Okay, so let's go through these conditions. So first we need exponentially large challenge space. Okay, it's fine because we have d over 2 degree of freedom. So we can pick any coefficients for these d over 2 coefficients, and the second half is uniquely determined. So we have 2 kappa plus 1 to the d over 2 elements. So to see, now we want to prove that sigma of C is equal to C for any challenge. And here we use the property that sigma is indeed sigma minus 1. So what's happening here? Okay, so if, for example, if I take C1x and I apply the sigma minus 1 automorphism, then x will be mapped to x minus 1, x to the minus 1, which is minus x to the d minus 1. So this means that C1x will be mapped to minus 1 minus C1 x to the d minus 1. And similarly, if I apply sigma to minus C1 x to the d minus 1, then by simple calculation, it will be literally mapped to C1x. So by construction and by this reflection or reflective property, we have that sigma of C is equal to C. And then we want to prove that a difference of two distinct challenges is invertible. So, okay, one could use this some facts that, okay, small elements over RQ are invertible, but instead we can use a slightly simpler observation, which says that if C is stable under the -1 automorphism and C is non-zero, then C is invertible. So that's like a nice, nice fact. Okay, so that's how we build the challenge space. And
can I ask you a question, Khanh?
Sure.
But don't you need C minus C prime to be invertible?
Oh, right. Yeah. C minus C prime. Yeah, that's a typo. Yeah. So we need the So the difference of any to.
Yeah. Is it just a typo in the observation? But it says C is invertible, but we need C minus C prime to be invertible.
Oh yeah, but obviously if C is stable and C prime is stable, then I see that you're confused with the notation. Maybe I should put C bar, because I think you think that this C is the same as this C.
Ah, okay, it's the difference of C's.
Yeah, it's like you could think of this C as a difference.
Mohammed, the difference of C and C prime belongs to the capital C again.
I mean, it might not belong because the coefficients might be bigger than kappa, obviously. But what we need is that the difference will be still stable under sigma. I think that's what you meant.
But the observation will not help you if C minus C prime, which is your C bar now, does not belong to the capital C, right? So how are you going to use the observation to show the difference of any two C and C, C prime is invertible?
Well, so C minus C prime is non-zero, right?
Yes.
Because C and C prime are stable under the sigma automorphism, then so is the difference, right?
This I agree.
Yes.
And then the observation follows, right?
But do you have that anything stable under sigma is invertible?
Yes, anything stable under sigma and non-zero is invertible. For that.
Okay. Okay, that's kind of like an external fact that you proved somewhere else. I thought that we were driving that observation, but okay, you're just getting that from somewhere else.
Yeah. It's like maybe not. Okay, maybe I should phrase it as a fact or something.
Okay, yeah, I see that. That makes sense. So you are saying that this fact holds. There is proof somewhere. Yeah. And then you are just proving that this if statement for your challenge space holds, which is the case.
Yeah.
Okay.
Thanks. Okay, so now we want to, we show how to prove one quadratic equation, but what about amortization and like proving many quadratic equations? Because if one were to prove each of them separately, then obviously the number of garbage terms would grow linearly in K, in the number of equations. So we can just, so this is like a standard trick. So we commit to S1 and M, and then given random challenges mu1 up to mu k, I just prove that the linear combination is equal to 0. which is then a quadratic equation. So because x to the d plus 1 split into these polynomials of degree d over 2, one can simply derive that the soundness error is q to the minus d over 2. So that's like a standard standard technique. Okay, I think I'm going to open the window because it's getting very hot. Hopefully it's not going to be very loud. Okay. Okay, so in the next part we show we prove these inner products over ZQ. So at the very beginning, for a warm-up, suppose we want to prove that the inner product of U and S1 plus inner product of V and M is equal to A over ZQ. So what do I mean by inner product? So when I say inner product, I say that it's an inner product over the coefficient vectors, not the inner product over RQ. So that, so yeah, everything is over ZQ. I'm talking about the coefficient vectors. So here we use the fact. So it has the proof, we will use it. So the fact is that the inner product of polynomial vectors x and y is the constant coefficient of the polynomial x transpose sigma minus 1 of y. So yeah, so the proof is just writing everything out, and then just writing this polynomial explicitly and looking at the constant coefficient. So there's nothing magical here. So how can we use this fact? So
can I ask something more? Sorry. So is this saying that if you take the coefficient vector of x and coefficient vector of y, do the inner product, then
yes,
this is
that's
the
what I mean.
constant coefficient of, if you do x transpose times sigma minus 1 y over RQ.
Over RQ, yeah, over the ring. Yeah.
Okay, all right, yeah.
So this is equivalent to proving that the constant coefficient of, and now I'm just using the fact, sigma u transpose S1 plus sigma v transpose M minus A is equal to 0. Okay, and for those who are familiar with the ENS paper, now it's just using the same trick. So now we just want to prove that constant coefficient of some polynomial is equal to 0. So what can we do is, well, we could just send that polynomial in the clear and the verifier could check that the constant coefficient is 0, but that would also leak other coefficients of the polynomial and that wouldn't be zero knowledge. So instead we commit to this masking polynomial G, which has the 0 constant coefficient. And then given a challenge alpha, we will output H equal to G plus alpha times that polynomial, which we want to prove that has constant zero constant coefficient. So we output that H equal to G plus alpha times sigma of U transpose S1 plus sigma of V transpose M minus A. Then the verifier checks that the constant coefficient of H is 0. And this will be the case, right? Because, well, the thing in the bracket has the constant coefficient equal to 0. Multiplied by alpha doesn't change anything. And then we have G, which has the 0 constant coefficient. So this verification check is satisfied. And we also need to prove, well, that H is well formed, that H is of this form. And well, you can see that it's doable because this is just linear equation over R cubed, where we committed to G, S1, and M. So it's a linear equation. Okay, so we can also see that the soundness error is 1 over Q because, well, if the constant coefficient of this thing wasn't 0, then, and the constant coefficient of H is 0, then there is only one alpha such that, well, which can make this check satisfied if we look at the constant coefficients. So the soundness error is 1 over Q, and the idea of ENS is basically to repeat this part of the protocol to amplify soundness. But yeah, we don't really have time to go into that. Maybe let me discuss a slightly more interesting case. So we want to prove inner products with 2 unknowns. So we want to prove that the inner product of, let's say, S1 and S1 and M is equal to A over ZQ. Okay, the fact still follows. we see that it's equivalent to proving that the constant coefficient of S1 transpose sigma of S1 plus M transpose sigma of M minus A is equal to 0. And we just do the same thing as before. So we commit to a polynomial G, which has the 0 constant coefficient. Given a challenge alpha, we output H equal to G plus alpha times this polynomial we want to prove the constant coefficient is equal to 0. So S1 transpose sigma of S1 plus M transpose sigma of M minus A. The verifier checks that the constant coefficient of H is equal to 0. And well, we prove well-formed of H. So I hope it's clear now that this is indeed a quadratic equation in the committed messages with the sigma automorphism. So that was the reason why we wanted to introduce the quadratic equations with automorphism, because then we can prove well-formed of H. So that's basically the idea. So what can we do now? Great, so we can prove arbitrary quadratic equations with automorphisms over RQ. We can prove inner products over ZQ. So let's say proving AS is equal to U over ZQ or RQ. Another interesting thing is that we can prove that the norm squared of the vector, which is the inner product of itself, is equal to B mod Q. However, we can see that it's not very interesting if we want to prove that the norm squared is equal to B, because, well, we only have this equation mod Q. But if we want to prove the norm of the vector, we should get rid of mod Q. So that's where we use approximate range proofs. So approximate range proofs allow us to, well, to deduce that even though certain equations hold mod Q, we can lift them and deduce them that they hold over integers. So more concretely, with approximate range proofs, we can convince the verifier that some short vector S, which has, let's say, norm B, satisfies norm of S is less or equal to some approximation factor psi times B. So why is it interesting? So let's have a look at this example. So we know, okay, so earlier it was B, now it's B squared. I hope it's not very confusing. So suppose that we prove that norm of S and S is, sorry, the inner product of S and S is B squared mod Q. But from approximate range proofs, we know that the norm is less or equal to psi times B. So now we can prove that this equation, that if Q is sufficiently large, then there is no modular wraparound going on. So that we can imply that, that the norm of S is indeed equal to B. So that's motivation. That's the motivation of approximate range proofs. So how do we do that? Well, the general strategy is using the fact that if S has large norm, then for a random matrix B, B times S should also have large norm with high probability. So the let's say naive idea would be just to send BS, prove that what we sent was indeed B times S, which is a linear equation, which we know that we can do it from the previous part of the presentation. And the verifier could just check that BS is indeed small, which would imply that S was also small. However, sending BS in the clear has the problem that it's not really zero knowledge. It might leak some information about S. So what we do is that we need to slightly modify the strategy and introduce the masking part. So we have this modified fact that if S has large norm and Y can be anything, then for a random matrix B, if BS plus Y also has large norm with high probability. So how do we make use of it? Well, we just send the commitment to the Y, well, to the S. The verifier sends a matrix B, and we send Z equal to Y plus BS. Oh, maybe I should specify it's mod Q. I mean, okay, this will be over integers. This will be over integers, right? The verifier checks that the norm of Z, that Z has small norm, which by this fact, it will imply that S has small norm. But in the end, we want to prove that Z is well formed. So we prove that Z is equal to Y plus BS mod Q. And we know how to do it from the previous part. So, okay, so how can we use these approximate range proofs? So the nice thing is that we can prove that vector S has binary coefficients, and that's without using any entities. So we use the simple observation. Okay, maybe again I should say it as a fact that S has binary coefficients if and only if the inner product of S and S minus 1 is 0 over integers. So for people who don't find it obvious, maybe this this explanation will just clarify it briefly. So if we look at this inner product, that it's a sum of Si times Si minus 1. Then obviously Si times Si minus 1 will always be non-negative if Si is an integer, and it will be 0 if and only if Si is binary. So now just by combining all these inequalities, we get that S has binary coefficients if and only if this inner product is 0 over integers. So that's we can use approximate range proofs combined with the inner product argument to prove that S has binary coefficients. And obviously the main motivation, proving that the norm is less or equal to some B. Okay, Mohammed, can, what time is it? Am I already like late?
I think you have about 5 minutes.
Okay, sure. Okay, so it's we can just combine all that stuff and then we get a nice framework. So in terms of applications, if we have a look at like a simple, some simple application like proving knowledge of the module LWE sample, something similar to the benchmark equation, then we get around 14 kilobytes, which is 2 times better than the prior works. And it's that's thanks to the fact that we don't really rely on the entity packing technique. We can use a more compressing commitment again, and also we don't need to repeat that much. So we get a factor of 2 improvement, and our framework can be applied directly to build some other primitives like verifiable encryption under 20 kilobytes. Then we have in the ongoing work, we have integer addition, multiplication under 15 kilobytes, group signatures, ring signatures, and then there's already one other paper which uses our framework to build blind signatures in less than in around 44 kilobytes. So because this work is new, I hope that this framework can be used in many other applications. I know that the Monash group is very interested in like blockchain applications and VRFs. Maybe it can be used there. So we'll see if this protocol can be used in many more advanced applications. So to summarize, well, we propose a new framework for practical lattice-based zero-knowledge proofs where we don't need to rely on the entity packing technique. So this comes with 2 main consequences. The first one is we have this compressing commitment, so it's fine for us to commit to long vectors. And also it's almost one shot because there is only one small part where we need to repeat. And that comes from the fact that we can pick a ring where x to the d plus 1 splits into higher degree polynomials. And if I were to pick one key idea of the paper, I would say that the inner product of x and y, which is when I'm talking about the coefficient vectors, then the inner product of x and y is the constant coefficient of the polynomial x transpose sigma minus 1 of y. So this is the key idea for proving inner products, modulo q. And then to lift the equations from mod q to over integers, we apply approximate range proofs. So that's basically the summary. So thank you very much. And I'll be happy to answer further questions.
Thank you very much, Khanh, for your very interesting talk. If there are any questions, you can either raise your hand or just unmute yourself if you're a panelist. While you maybe think about the questions, I'll just ask, well, I'll start with a simple one. So for this key idea, this only holds in the specific ring that you specified before. This Q is 5 mod 8, and that's concrete splitting, or?
No, it holds over like without mod Q.
Okay.
Yeah.
So that specific challenge space, you only use that so that it's stable under automorphism.
Exactly. So yes, so the only place we use that Q is 5 mod 8. Apart from having this, is for this challenge space. And that's this observation that this fact, which I called observation, it holds only 5 mod 8. At least the proof works for 5 mod 8. Well, I'm pretty certain it can be applied to like more general case, but at least for our framework, we can just pick 5 mod 8.
And is Q prime? Do you need it to be prime?
It's Q prime. Okay, so in all these in the whole talk, we assume kind of that Q is prime, but this protocol can be generalized with like a composite modulus. So let's say if the modulus is a product of all these Qs, which are 5 mod 8. That's what we do in the paper. So usually in the paper, so in our applications, Q will be either prime or it will be a product of 2 primes.
Okay, I see. There's also, I guess, no loss or no expansion if you want to represent the witness in the, right? So if you put the witness in the, let's say, NTT coefficients, since you only have 2, then you could only put 2 coefficients. But now, since you are not doing that, like if X has D coefficients when you look at it as an RQ polynomial, still in the inner product, D coefficients gets multiplied. So there is no loss in terms of that kind of like, or there is no expansion to represent the coefficients in this inner product, right?
Yeah. I think, and I also think that it's kind of the most natural approach, right? You want to commit, you have the polynomial, you have some vector, binary vector, and you just put it in the coefficients of the polynomial.
Right? Yeah, that's right. That's because in the NTT packing techniques used in the earlier works, and if you split into, I don't know, 16 fields, then you can only store 16 coefficients, right? There is no more space to store things. But okay, there is a question in the chat from Russell I. Can you comment on why the difference of challenges C minus C prime only needs to be invertible over RQ, but not R?
Can you comment on why the difference of challenges C minus C prime only needs to be invertible over RQ but not R? Just go to that slide. Okay, maybe the easier thing would be to, let me just check if which slide is like more appropriate to refer to. Sorry, I think my slides are lagging, so. So this is like a standard thing in the approximate proofs, or like Schnorr type proofs. So we prove, so it is, okay, so we need the challenge to be invertible over RQ because, well, it's being used in the opening proof. So so it's fine to use, okay, so maybe, how to say it? Okay, so we had this ABDLOP open, BDLOP commitment, and we talked about the being binding. So obviously being binding is like not really what we want in practice, because when we do the opening proof, then we don't really obtain the full commitment. We don't really obtain S1 and S1, S2 and M, where S1, S2 are small. Instead, we get that C times S1 and C times S2 are small. So I hope this is familiar. Yeah, this sounds familiar, I hope. So then we define this weak binding notion where where the weak opening is S1, S2, and M and C, such that C times S1 is small and C times S2 is small. And C is invertible over RQ. Why is it? And why do we need that C is invertible over RQ? Because it's kind of hard to say it without writing anything. We need
I guess we kind of want a unique solution for M, right? If challenge difference is not invertible, then there is no unique M that you can extract, because I mean you get something like this, right? So let's suppose you put, let's say, C bar here,
yeah,
and then you get an expression of this form. Let's just ignore this one for now. You get an expression of this form, especially the bottom part, right?
Okay.
Then if C bar is not invertible, then you cannot extract a unique M, right? Because for certain entity coefficients, if they are 0, then any M that you put into that entity coefficient when you run the proof, then that will hold, because you are basically proving that 0 is equal to 0, and you can use any M here. So imagine this is also like C bar M, right?
Yeah,
or,
I think
also C bar here. Then you can make the equation hold for any M that you choose, because you're just proving that 0 is equal to 0.
So I think Russell's question was more like why we need a C bar to be invertible over RQ, and why is it fine to be over RQ and not over R? And well, the idea is, well, because everything here holds over, it's over RQ. So
Russell, by the way, you can speak as well. I allow you to speak if you want to.
Hi, can you hear me?
Yes,
yes.
yes, we can hear you.
So if C minus C prime is only invertible over RQ, then it, like, the difference might be large. So it's a large element in RQ.
Yes.
And
yes.
And so, like, so this gets multiplied to the extracted witness, and that means the extracted witness will be large if you don't do something else to bound it, right?
Yeah. So the thing is that what we know that this C bar times S. Let's just focus on S1, okay? So we know that we know we have some C bar, okay? C bar is invertible over RQ. So I know that C bar times S1 bar that I extract, C bar times S1 bar will be small, because that will be the difference of two Z's or something. This S1 bar will not be small. So that's what you said. Do we agree so far?
Right, yes.
So
yes.
So the thing is that, okay, we don't know that S1 is small. Sorry, S1 bar is small from these equations, but we can still do these operations. So like I can prove that the inner product of S1 with S1 is something mod Q. So that's what I can still do, right? And then to prove that the S1 is indeed small, S1 bar is indeed small, that's the part where we use this approximate range proof to prove that it's approximately small. And then approximate range proof combined with the inner product of S1 and S1 equal to something mod Q, we can deduce that the norm of S1 will be small. So I hope, yeah, let me know if I should repeat any part, if it was too fast.
Okay, so, and is this something that one cannot do in the bulletproof setting? Because there one has to choose the challenges so that the differences are invertible over R instead of RQ? Or if this is going too far off track, we can take it offline.
So I was thinking about this technique in the bulletproofs. So what you have in the bulletproofs is that you kind of explicitly I mean, okay, so what you end up with is that you know that as in the bulletproofs, you would get some S1 bar, but you know that S1 bar times the determinant of this van der Waals matrix is small, or something like that.
Right.
And this factor which is in front of S1 bar, it is very I mean, this thing dictates the sys hardness of the whole commitment, if it makes sense. So I think it can be used, but I don't think that there would be any. Okay, so I think this overall technique can be combined. So but I haven't I haven't got any progress in like any obvious improvement using this analysis applied to bulletproofs.
Okay, thank you.
Thanks.
Any other questions from anyone?
May I ask a question?
Yeah, go ahead.
Sure.
Please.
So you heavily relied on the fact that you use this sigma being sigma -1, right?
-1. Yes.
But there are so many other automorphisms, right, in the Galois group of this RQ, right?
Yeah.
Have you ever wondered, I understand later on you're going to use that fact that the inner product is just the constant coefficient of x times sigma y, but rather than these two facts, I think if you just simply replace sigma by any other sigma, it should work, right? Rather than the observation. So does the observation that you had for the difference of challenges still work for any automorphism? For example?
Okay, so first of all, yeah, so let's, where is this?
Yeah, so my generic question is, what are the challenges if you just change sigma, your sigma to any sigma?
So first of all, we would, if we want the C to be stable under, let's say, any automorphism, then preferably we want this automorphism to have small order, because then we can see that if the order was big, then it would be harder for us to pick large challenge space. So maybe this first step, is it clear? So, okay, so it is nice for the -1 because the order is 2. So we have d/2 degrees of freedom. So that's nice.
Yeah.
I think that, okay, so now if your question is, okay, just pick any sigma which has order 2, can we do that? So I think these all these results could be generalized to any sigma of that form.
Does this inner product fact still hold for other sigmas?
So for other sigmas, I guess you would need to like rearrange the coefficients first, I guess. But I guess for presentation, sigma -1 is the most suitable because we already deal with the coefficient vectors, right? And the sigma -1 works for these inner products over these coefficient vectors. But Amin's question was like if we can just generalize to any sigma. So I guess if we generalize to any sigma, then obviously these facts need to be changed.
Yeah.
In terms of this fact about this invertibility of the challenge space. Yeah, I'm not sure. I haven't looked at any generalizations of this fact yet. So, but I would guess maybe.
So going back to that observation or the fact that we discussed already, this one. So is this is this a stem from characteristics of RQ, right? Being like
yeah,
Q being 5 mod 8 and
yes,
okay.
it relies on the fact that it's 5 mod 8, but I wouldn't be surprised if there was any if there was like a more general result, but just for 5 mod 8 you can just compute everything directly, I would say. So
and one simple very simple observation of these sort of polynomials is that x equals 1 is a root.
Sorry, could you repeat?
So another observation of such polynomials belong to this capital C set that you have is that x equals 1 is always equals to C0, right? Because they cancel each other, right?
Yeah.
I don't know if it's a fact that can be used, I don't know, to make a scheme more efficient or make some attacks possible to this. But like the moment you put more structure into things, I start to think, yeah, maybe something is because these self-reciprocal polynomials have a lot of other, for example, characteristics and functionalities rather than just the ones that you used here to have the observation and being a stable over sigma. But yeah, I don't know. You didn't have a look at that from that angle, I'm pretty sure. It's
no.
You made your way out of it because you wanted them to have these characteristics.
Yeah, basically. But it is definitely an interesting area to investigate.
Yeah. Okay. Yeah. So, for example, I would definitely start looking at all these equations that you try to prove and put x equals 1 and see what's going to happen. Is it something meaningful you will get out of it, or is it going to be just I don't know, maybe going back to the rings rather than modules? I'm not sure. Or being on integers, that I'm not sure.
Yeah, maybe this fact can be used.
Yeah, that was just a side probably comment. Yeah, thank you.
Any other questions from anyone? Okay, maybe I'll just ask one last quick question. So in the comparison that you had at the very end, where you said that like you almost halved the proof length, is that for are you proving L2 norm or are you proving L infinite norm for the secret?
So I'm proving the L2 norm.
Okay. Yes. Okay.
So there are also like other things which are kind of hidden, but you couldn't do it with entity packing proofs anyway. So for example, if I want to prove that so I want to prove that AS plus E is equal to U, and S and E have small norm. Okay. So so the nice thing with our quadratic proofs, or like with our framework, is that you can prove AS plus E is equal to U and S and E have small norm without committing to E. So you prove that S has small norm and U minus AS has small norm.
Yeah.
So that's why you don't commit to E, and here you have even
is this already, like, this optimization is included in the 14 kilobyte or?
Yeah, it is included in 14 kilobytes.
So kind of technically for the last one, the secret dimension is something like 1024, not 2048.
Yeah.
Okay. Yes. All right. Yeah.
But because it's the commitment is compressing, then if you were to commit to also E, then it wouldn't grow that much.
Yeah.
At least.
I see. Okay. All right. Yeah, I think for the sake of time, we may conclude the session here. So I'll just show this concluding slide. And thank you very much, Khanh. This was very interesting, and definitely, especially for me, as you know. Thank you, everyone, for tuning in. Hope to see everyone in the next talk. And thank you again, Khanh.
Thanks.
Thank you. Bye.
Thank you.